The 3D model we build is a physical model with actual member size is rendered. The analysis converts the physical model into the analytical model, as shown. The analytical model is a centerline wireframe model. Alternatively, slabs can also be meshed and included in analysis. After a successful analysis, analytical model must be checked rigorously to ensure the model and result is correct. First and foremost, ensure the physical model is converted correctly into a valid analytical model. After successful analysis, go to Post-Analysis tab. Click Display Analytical Model. Alternatively, if the Building Analysis dialog is closed, you can go Analysis tab, click Analytical Model. The Analytical Model view will open. A new Analytical Model ribbon will appear, with several tabs at the top. The analytical wireframe is shown in blue. The darker blue line is the rigid beam of the shear wall due to mid-pier assumption. The displacement are automatically shown as red lines. Deactivate displacement under the Result tabs so that we can focus on the analytical wireframe. You can rotate, zoom in and out, or move it, similar to any 3D view. On the right pane, all the load cases and load combinations are listed. On the left pane are stories, axes and member types filter. The model you created is a physical model with actual member sizes rendered. The analytical model is what is analyzed and solved. Hence, the first step is to verify that all elements are connected together by checking all the blue wireframe are connected together. If the view is too congested, use the filter functions to filter to say story 4 by unchecking all stories and then checking story 4. Then zoom in to check say the primary and secondary beams area. Once zoomed in, the red cube joints can be seen. Verify if members are connected together to a common joint as intended. Show all stories and zoom out. Go the General tab. Click Settings. Here you can adjust the analytical view settings such as font size and color. There are many tabs, such as Node, Frame, Shell Settings, etc. Click Cancel without changing anything. Click on the Plan icon to lock to Plan View. Click again to unlock. Click on the View icon. A view cube will appear at the top right. You can then click on the face, edge or corner of the cube to change the viewing direction. Click the View icon again to switch it off. You can save this view as a picture file, or copy and then paste somewhere else, say Word document. The Find command allows you to find a particular node, frame or shell number. Type in node 1 and click Find. An arrow will appear pointing to the node. Click Clear to clear it. The filter pane is by default turned on. You can hide it by clicking on this icon. Toggle it on again. Connectivity Issues automatically lists all the frames with unsupported nodes and highlights it when selected. Click on it. A message saying there are no connectivity issues detected. OK. Currently, we are viewing the linear analysis. Click the Members tab. This is where you can show or hide node labels, rigid diaphragms, element labels and beam loads. These icons are self-explanatory. Click on them to experiment. Example, turn on and off the node labels. Click on the diaphragm icon. Various choices are exposed. D1-1 means story 1 diaphragm. Since there are 4 stories, 4 diaphragms can be shown. Choose all. Filter to story 4 only for clearer view. The diaphragm are formed by interconnected slabs, according the default option, slabs to define diaphragm. The gray line shows the extent of the diaphragm, joining nodes that are constrained by the diaphragm. The lines all joins to the center of diaphragm, which is also the center of mass of the story. Switch off all the diaphragms by choosing Deselect All. Click on Frame Labels to turn on the actual member labels, which is very useful. Click Frame Loads icons to show loads calculated or decomposed on the beams. Currently, Load Case G is selected in the right pane. Hence, the frame loads will include all the slab loads, brick wall loads, beam self-weight, and other manual input loads. Click on Frame Load Labels to turn on the values. It is very important to check the frame loads. Use simple logic by comparing values of different beams based on what is applied. Firstly, since all beams in the roof are supporting slabs, and slab loads are calculated by yield line or area tributary method, all beams should have a triangular-shaped frame loads. Secondly, since all the slab thickness are similar, the loads values should also be similar. Next, look for anomalies, such as sudden change in values. As you can see for this perimeter beam, RB10, there is abrupt jump in loadings. This due to partial cantilever slab supported by this beam. If slab are included in meshed and building analysis, you should check the shell pressures values applied. You should go through each load case in detail. Next, choose Q load case, which is the life load case. Similarly, check if the applied loads are correct. To get a less cluttered view, go to Members tab, turn off member labels. QP11, 12, etc. are all pattern load or load arrangement cases. In total, there are 10 cases. Zoom out and click these pattern load cases one by one. As you can see, these load patterning is loading the adjacent spans and also alternate spans. Moreover, this is performed in direction 1 as well as direction 2. Hence, load patterning is done rigorously to capture all possible permutations.
Click Nodal Loads to ensure that this load type is displayed.
Next, choose NGX load case. This is the notional or equivalent horizontal load case. This was defined in the settings, lateral load dialog, based on percentage of dead and/or life load. The load is applied to the center of diaphragm for each story. There are a total of 4 equivalent horizontal load cases for dead, life load, and their respective X and Y direction. Filter to show all stories. Check these load cases one by one and satisfy yourself they are correctly applied in the analytical model. These values should tally with the values found in wind and story loads dialog, which will be populated after analysis. Similarly, check for wind load, WX and Y load case. Since lateral load transfer is by rigid diaphragm, it doesn't matter if the wind load is shown to be applied at the center of diaphragm or at edge of story, the net result is the same. Generally, check all frame and nodal loads for each load case one by one to ensure the input loads are correctly applied in the analytical model before even looking at the results. As we are well aware, wrong input equals wrong output. In other words, rubbish in equals rubbish out. Once you are satisfied, go back to the Members tab, switch off both the frame loads and frame load labels.
In the latest version, there is new function to show the support reactions. Click on Support Reactions. Zoom into the support to see the support reactions with respect to the global coordinate system. Disable it, zoom out.
We are now ready to interrogate the results, such as the displacement and member forces. Go to the Results tab. Click Displacement. Select G, Load Case. The red line shows the displacement or deflected shape of the structure on the selected load case. By default, Autoscale is activated. You can deactivate this and then type in your own scale, if desired. Click on the various global directional displacement values. The convention is shown in the global compass in the lower left corner. X is global horizontal plan displacement. Y is global vertical plan displacement. Z is global displacement along the story height. R is the resultant value in 3D space. Rx, Ry, and Rz are rotation of joints in radians. Activate R to show the resultant magnitudes. Switch off the displacement values for a less cluttered view. The maximum and minimum displacement is shown at the bottom of the screen. Click on this legend, and an arrow will appear to pinpoint the node of maximum displacement. Click Animation to visualize the deformation of the structure better. Bidirectional animation, exaggerate the displacement in both directions. Try deactivating bidirectional and observe the difference in animation. Don't forget to check other load cases. Select NGX, check and satisfy yourself that the displacement is reasonable and expected. Similarly, check displacement of WX and WY. As a summary, ensure that you check displacement carefully for each load case. Unreasonable deflection may mean the model is incorrectly set up. Unreasonable deflection will lead to unreasonable member forces, as the displacement is a direct reflection of the forces a member experience. Switch off displacements display. Click on Geoload case. Click on Diagrams button. By default, axial load N will be displayed. As expected, the axial load of columns and walls increases down the floors. For a less cluttered view, let's filter to Story 4 and look at the other force diagrams. V2 is the major shear force of beams and walls. It is the shear of column along direction 1. V3 is minor shear force of beams and walls. It is the shear of column along direction 2. M22 is the minor moment of beams and walls. It is the moment of column along direction 1. M33 is major moment of beams and walls. It is the moment of column along direction 2. T is the torsion of all members. Labels will toggle on and off the force values. You can change the diagram scale by deactivating auto scale and typing the desired scale. You can turn on or off the diagrams on column, shear walls, beams, and rigid link by clicking on the respective icons. Click Properties. Click on M33 Force. Then click on any element. The Properties tab will be populated with useful information on the analysis assumption, such as the section properties and analysis forces at element ends. Click on the drop-down triangle to expose more information. Click Properties again to turn it off. We should continue to investigate the force diagrams for lateral loads. Choose NGX. Under Diagrams, choose N for axial force. When looking at lateral loads, it makes more sense to turn on all stories. Let's look at the core wall axial loads. As you can see, vertical walls are in tension and the horizontal walls is in compression. These forces make perfect sense, as the NGX lateral force is pushing the building in the global X direction. You can continue to investigate the other lateral load cases, such WX and WY. Generally, we should interrogate the force diagram based on the deflection and movement of the structure or the expected behavior. Then it becomes much easier and logical to explain the forces and detect any anomalies. Go to the Contours tab. Contours tab is only relevant if we have used shell elements, that is, if we have used finite element shells for wall model, or if we have included and meshed the slab and building analysis. Since we have used none in this model, there will be no contour results to view. Go to the Solid Model tab. This allows the various effects such as axial stress, shear stress, etc. to be color-coded on the physical model, rendered with actual member sizes. Select Geoload case. Try exploring some of the effects. To exit the analytical model, you can close the view by clicking on the Close icon. Alternatively, if you want to access this view again later, you can click on another view, such as the Plan view. Click on the Plan view. Here is a summary what to check an analytical model. It is essential to carefully examine and verify the analytical model. First, check the analytical wire frame. Are members connected properly? Is the analysis model created accurately based on what you model? Check the loadings on the model for each load case by switching on nodal and frame loads. Are all the slabs loads calculated correctly onto the beams? Are user-defined loads applied correctly to members? Are all the lateral loads, example, notional and wind loads applied correctly? Check the displacement shape and magnitude of the model for each load case. Displacement is a reflection of the forces members experience. Unreasonable displacement indicates model forces will be wrong. Check member forces for each load case. Verify axial, shear, moment and torsional forces are reasonable. If in doubt, turn on the displacement as well for better visualization. Do not proceed to design of members until fully satisfied the analysis is correct.